So remember what we said before. To basically do mass spec, you need to rely on the fact that you've got a particle and it needs to be charged and moving. Now, we did work earlier with an atom and it wasn't charged, and we charged it up, we ionized it, and we accelerated it, and then, you know, we made it undergo circular motion, and that was the gist. Now, for your course, it's really more about molecules that you're going to be tested on.
Yeah.
Are molecules charged?
No.
No, they are not. So they'll undergo the same problem. You'll need to make them charged. And that's not too difficult, because molecules can be like ions. You can basically ionize them, and then you can accelerate them. So in some ways, the molecule you can think of in some ways just as a bigger atom. All right? And so it's just a bigger thing, and it will do its thing, just like an atom does. But there is a level of complexity that molecules end up bringing to the table and adding to your problem that atoms do not. So take, for example, propane. Now, is propane a stable molecule?
Yes.
It is, right? It's quite stable. But when you put propane, for example, in a mass spectroscope, it's going to be ionized, right?
Yeah.
Which means it'll lose an electron, yeah?
Yeah.
And for all intents and purposes, just assume that you will always only lose one electron, and your positive, like we said, it's mass to charge ratio, which is correct, but for your purposes, always assume the charge is +1, all right?
Yeah.
So it'll lose an electron. And it'll become positive, right?
Yep.
Now, is this stable?
No.
Not really. It's not very stable. Exactly. So now, granted, you know, one of these bonds lost an electron. Doesn't matter which one, right? But it's one of them.
Yeah.
Now, granted, mass spec, they're moving at very fast speed. So maybe it just gets to the end and gets detected anyway. Just like we said, nothing happened, right?
Yeah.
But because your M+ is not stable, your molecule is not stable, it's very possible for it to split into different parts, called fragmentation. So you could perhaps get A plus B, B plus, or you could even get, you know, A plus plus B. So we don't know for sure what happens because it's all probability based, but let's say I broke it there. Then I'm going to get a fragment, which is your CCHHHH, and I'm also going to get a fragment, which is CHHH. And one of these will have the positive charge, and one of them will not.
Yeah.
Now, it could be either. It depends on the situation. Does that make sense?
Yeah.
So this is molecular fragmentation. All right. So with that understanding, if your molecule breaks up before it gets to the detector, will the detector detect the molecule?
Yeah.
If you start with a molecule, but it breaks up before it gets to the detector, will the detector detect the molecule?
No.
Or will it detect the pieces?
The pieces.
It will detect the fragments, right?
Yeah.
So whenever you're doing a mass spec, you get a readout, and that readout would include potentially the whole molecule minus an electron, right?
Yeah.
Most certainly could have that, and probably will have that, because you have to remember, you're not putting in one molecule, you're putting in a sample which is like lots and lots and lots of molecules, right?
Yeah.
And so some of them will break up, or in fact, most of them will break up, but many there will be quite still a decent number that make it there without breaking up just by sheer numbers, right?
Yeah.
So you'll get that, but you'll also get the ones that break up. And, they could have broken up somewhere else. You could have broken off at H, right? But if you broke it off here, it would just be the same thing in reverse, really. But I could have broken off on H, for example, right?
Yeah.
And that's why mass spectroscopy of molecules is relatively more complicated, because you have to consider about the different types of pieces you could get out of that. Okay?
Yeah.
But the point is, if you can identify the mass to charge ratio of the fragments, then they give you a clue as to the original. So for example, if I told you I smashed up an object, I don't know what that object is, but I smashed it up, all right?
Yeah.
And you, as an investigator, get some pieces. You've got a steering wheel. You've got a tire. You've got some glass, right?
Yeah.
You've got a light bulb. What do you think this original object might have been?
A vehicle.
Yeah, it's probably a vehicle. You probably don't know exactly what brand of vehicle it is. You probably, based on my description, don't know, was it a truck or a van or a car? It's probably not a bicycle because you had a steering wheel, but, obviously I could have been more specific about the wheel and the tire. And if I got a wheel that had a particular brand on it, then I could probably tell the brand, right?
Yeah.
If my steering wheel had the brand on it, I could probably tell the brand. If my wheel is particularly big or small or wide, I can probably tell if it's a bus or a truck or what type of vehicle. Is it four-wheel drive? Like, I didn't give you any of those details, but you get the idea, right? Based on the little clues we get from the pieces, you have some idea of what the original was, right?
Yeah.
So that's exactly what your mass spec is doing, right? Your mass spec in this case is basically, you put in a sample, and inevitably some of the sample will break up. And from those breakup fragments, as well as the ones that get through in the hole, you will know their mass to charge ratios. And you also know how many, of each one. And then you can basically essentially work out, from potential sort of fragments, what was the original structure. And that's basically sort of how you do that.
Yeah.
So we'll look at sort of questions now. And just so you know, we won't be looking at NMR today, but for next week, we'll be considering,
Yeah.
the design and, questions that NMR is designed to sort of handle. Yep.
Yeah.